Okay, hi. This video is on how objects charge, so a couple different ways of charging, and a term called conservation of charge. So the basic of charging, one of the most fundamental ways of charging, is through conduction. So it's just when two objects touch each other, typically conducting objects, or at least objects that conduct to some degree, could be semiconductors, electrons flow from one to another. Remember, protons typically aren't moving, it's usually electrons. And conservation of charge tells us something's conserved. It means it's not changed. So the total charge is unchanged, meaning all those protons and electrons still exist, they don't go away, and the total charge is unchanged. So take a look at this example here. Let's say we have two objects. One has a charge of plus 3 coulombs, and one has a charge of negative 3 coulombs. And if you add up the total of plus 3 minus 3 equals 0 coulombs. So when you touch them together, you're going to end up with two objects that are neutral, both with 0 coulombs on them. You could separate them at this point, and if you separated them, they'd still have 0 coulombs and 0 coulombs. So even though the individual charge has changed, the total charge did not, the total is still 0. If you look here, to go from negative 3 to 0 means that it lost electrons. So electrons must have gone from here to there. That one went from plus 3 to 0. That means it gained electrons, gained negative charge. So this one gained electrons. This one lost electrons. This was a kind of basic example, but imagine this instead. I'm going to go for let's try to be consistent with these. Instead of having plus 3 and minus 3, I have plus 3 and minus 5 coulombs. And we touch them together. And we know that the total charge, plus 3 minus 5, has got to be equal to negative 2 coulombs, right? That doesn't mean that there's negative 2 coulombs on each of these objects, though. If there's negative 2 on each, then you'd have a total of negative 4. So that total is split among the two. So each of them get minus 1 coulomb. And once you've done this, it's more or less irreversible process. So after you separate them, they still have a charge of negative 1 coulomb. Negative 1 coulomb. This one went from plus 3 to minus 1, so it gained a whole bunch of electrons, gained a lot of negative charge. This one has gained positive charge, so it lost a bunch of electrons. Electrons went from here to there. So generally speaking, when we say electrons flow from one object to another, they flow from the more negative to the less negative object. Let's now take an example that's a little bit more complicated. Let's say that we have 3 objects, and we could touch them together. Now, there's different ways to charge them, we'll see. So imagine the first one is we just take the first two, the negative 3 and the plus 5, and we touch them together, and we leave that other one separate. So negative 3 and plus 5 have a total charge of plus 2, but that's split among the two sides, so each side gets plus 1 coulomb, plus 1 coulomb, and this one still has plus 3 coulombs. Let's separate these now. So we have a plus 1, we have a plus 1, and now let's touch this plus 1 to the 3. We're going to touch those two together, and the total of plus 1 and 3 is plus 4. But that plus 4 is split among two objects. So now you get a plus 2 and a plus 2. You could separate them. Minus 1, plus 2, plus 2. So depending on how you touch these objects together, they may or may not all have the same charge. If you touch these back together, you get no charge flow because they have the same charge. But if you touch the negative 1 and the plus 2 together, there would be charge flowing. There'd be electrons going from there to there. They would have a total charge of plus 1, so a half coulomb on each, for example. There's different ways to do it. Let's say instead, though, we go like this, and the same 3 objects, and we just touch them together like this. when any objects are touched together, there's no outside influences, the total charge will be split among all three. So the total is -3, +3, and a +5, so the total is a +5 coulombs. Split among each of them, that means they each get 5/3, but 5/3 is 1.67 coulombs. So 1.67 coulombs, 1.67 coulombs, 1.67 coulombs. We pull them apart, more or less irreversible, and then we each have 1.67 coulombs. So that's kind of the fundamentals of charging by conduction. There was another method of charging as well that we're going to talk about, and that is called charging by induction. So induction is not necessarily when you touch two objects together, but it's when you have objects and you bring another charged object near it without touching it. So right now we have two conducting spheres that are next to each other, but they're both neutral, so there's no charge flowing. They both have some positives and some negatives on them. You're not going to induce a charge separation on these because they're both both neutral. So instead, what we can do is we can say we're going to induce a charge separation by bringing a negatively charged object. I tend to use lots of rods and spheres for some reason in this class. Negatively charged object near this without touching it, right? If we touched it, that would mean that some of the negative from here would go over there, and these objects would end up negative. This would be negative as well. You'd get some repulsion, etc., etc. I'm not going to break it down too much, but we don't want to do that. We don't want to touch these. These objects still maintain a total charge of 0. But what we find is that because the electrons in these objects are repelled by the electrons in this rod, you end up getting electrons moving from the left side here to the right side. So you get a bunch of electrons. That leaves gaps here, such that the left side is positive and the right side is negative. If you remove the rod, all of the protons and electrons would go back to the way they were before. Like if you remove the rod, you'd go back to plus, minus, minus. However, if you don't remove the rod, if you actually separate these two objects first, separate them a little bit, doesn't have to be a lot, just a little bit, then charge can no longer flow through conduction between the two objects. So now we have a positively charged object and a negatively charged object. And now if we remove the rod, we still end up with a positively charged and a negatively charged object. So we've effectively charged these two objects through induction. We have brought a negatively charged object near them, caused a charge separation, and separated these two, and you have a negative sphere and a positive sphere. You would distribute those positive and negatives a little more evenly. So this is what is called induction. And you see this in a few different forms. Imagine, if you will, instead of that kind of induction, imagine instead you had an object like this that was maybe positive negatives, so this could be neutral. And you brought a negatively charged object near it, or a positively charged. Let's switch it up and do positive this time. And initially it would have a, if it got near that, it would have, you'd induce a charge difference on this, so that you're going to end up with electrons all going to the left side here, and protons going to the right side. If you brought the rod away, it would go back to the way it was before. Unlike in the last example, though, these electrons don't have any place to go, but if you can add a wire to this, the wire gives those protons a place to go. So total charge is conserved, but it's actually leaving the system. So these protons all flee, and they go away, and they go, and they run away, and then you're left with a negatively charged object. So your positively charged rod, your negatively charged sphere. Now, if you brought this rod away, you get a bunch of electrons running away, and this would end up neutral again. But if before you take that away, you cut the wire, you don't give those protons, well, you don't give those electrons any place to go, right? So now you can take away this, boom, and your object that was neutral is no longer neutral, it's now negatively charged. We're going to often measure charge with objects that we call electroscopes. And an electroscope looks a little bit like this. You might have even used one already in class. And it has two leaves at the bottom, and those leaves are attached to each other. So imagine this whole electroscope was positively charged. What happens is, if it's positively charged, those two objects will repel each other, and so the leaves of the electroscope will get wider apart. However, if the electroscope is neutral, then those leaves are going to lay right next to each other like this. And if it's negatively charged, there's going to be a big separation again, because they're going to both be negatively charged and thus separated. And you can charge something like this with conduction. You could bring a rod like this, put up a positively charged rod. You could touch it here, and you'd end up with this, because you'd have positive charge basically that went from the rod to the object. But instead, you can also approach this in terms of induction. So imagine this, you had like a positively charged rod here, and you had your electroscope, which might have been neutral at first, but when you put that positively charged rod near it, you end up with a bunch of negatives up top, and you end up with a bunch of positives down below. And those positives repel each other, so you end up getting a big charge separation. The same is true if you have a negatively charged rod. Looks the same. This is one of the tricky parts about understanding how to use an electroscope, because bringing a positive or a negative object near the electroscope will induce the same results. The charge distribution is different, but you can't see the actual charges on the electroscope. You can't see which are protons and which are electrons. You can only look at the result. However, if, for example, let's say you brought a positively charged, let's say you brought a negatively charged rod near that one up there. The negatively charged rod is going to drive some of those electrons in the top down here, so the bottom gets more negative. And so more negative is going to actually separate them even more. If instead you had a positively charged rod, the positively charged rod draws electrons up here, so the bottom becomes, even if it's negative, it becomes less negative. And if it's less negative, the leaves will get closer together. So it's a tricky business understanding how electroscopes, and I'll write this down, electroscope is a tool for measuring or detecting. I'm going to use detecting because it's really, you can't measure specific amounts. Electric charge. It's a tricky business understanding this. One last thing, and this will be quick because I know this video is getting a little bit long, is we've talked about charges in terms of, opposites attract, And we've said like charges repel. But what about neutral, huh? Well, in theory, neutral objects shouldn't be attracted to charged objects. Right? It's only if the charges are opposite, they shouldn't be attracted or repelled. I didn't put repelled in there. But I'm going to say there's an asterisk here. And that's unless you have induction. And so imagine this. Let's say we have our neutral object, plus minus, and we have a positive object here. Well, in this object, when they become close, if these are conducting, then you end up with a bunch of electrons over on the left side, which leaves gaps. So your right side becomes positively charged, and your left side becomes negatively charged. And the interesting thing that we find is when this happens, even though this is still neutral, and this is positive, you actually do get an attraction between them. And that's because the attractive force between the positive charge and the negative charge is bigger than the repulsive force between the positives and the positives. So the attractive force is bigger than the repulsive force. And this gets into something that we're going to talk about in the next video. And it really goes with the distance, sort of similar to gravitational force, the distance theory of forces like this, in that they are closer together. So the attractive particles are closer together than the repulsive forces, which are further apart. And we see that distance has an important effect on forces like this, like with gravity. So if you're closer together, you're going to have a slightly bigger force than if you are further apart. So you can actually get an attractive force between a positive and neutral object. I think that ends this particular video. Thank you very much for watching.